Hi everyone, and welcome to our first video in our new YouTube playlist on Students' Insights. Now, I'm very excited to be here with Julian and Max, whom I had the pleasure of meeting 6 months ago in a seminar that we offered on machine learning and finance. Now, Julian and Max prepared a screencast for you on artificial neural networks, how it works, and also how you can use that in your financial day-to-day work. Now, before we jump into the video, let's take a second to learn a little bit about the background of Julian and Max.
Hi, my name is Max. I'm currently studying business mathematics at KIT in my master degree. I'm focusing on computational risk and asset management as well as stochastic analysis. And I had already the pleasure to participate in a few courses of Professor Ulrich.
Hi, I'm Julian and I'm studying industrial engineering and management here at KIT, also my master's degree. In my studies, I'm focusing on data science and machine learning in a variety of industry applications. And I'm currently writing my master thesis on convolutional neural networks for food recognition.
And one thing I want to mention explicitly, I really thank you for putting up so much work with that screencast and also for sharing that work with a broader audience at our YouTube channel. So, which means if you like the video, which I'm sure you will, thumbs up to the video and also subscribe to the channel to stay informed on what's new on computational risk and asset management at the KIT.
Welcome everybody. During the next minutes, my colleague Maxime and I, Julian, will give you an introduction to artificial neural networks, or in short, ANN. This presentation represents the first part and should be followed by the second part of our colleague Manuel. So, let's get started. First of all, let me briefly show you the relevance of this topic. In recent years, remarkable breakthroughs have been achieved that were only made possible through artificial neural networks. For example, energy consumption is one of the world's most challenging physical problems. The amount of energy consumed by big data centers has always been a headache for tech companies. However, Google's artificial intelligence unit DeepMind applied a system of neural networks to operate data centers and managed to cut data center cooling bills by 40%. Given how sophisticated Google data centers already were, that's a phenomenal step forward. It were achievements like these that fueled huge interest in the area of machine learning, as can be seen here in the Google Trends history for the term machine learning neural networks. More and more people want to know what's actually behind this buzzword. And that's where we jump in with this screencast. Our goal is to start right at the beginning and provide a comprehensive introduction to the topic by shedding light onto the following three areas. First, the origin, second, the architecture, and lastly, about learning. So let's start where the artificial neural network had its origin, the human brain. The smallest logical unit of a neural network is a neuron. The neuron can be split up in three parts: an input, a processing and calculation, and an output part. The input part is called dendrites and acquires continuously stimuli from other neurons of the environment. The core, where the processing happens, is called soma. Here, so to speak, all the signals received from the dendrites consolidated and summed up. When a certain potential threshold is exceeded, an impulse is triggered, as highlighted here with a red dot. The output part is the axon and guides the emitted impulse to other connecting neurons. These three core parts of the biological neuron, namely the input, the processing or calculation, and the output part, can also be found in an artificial neuron. Inputs C are fed into the cell body, where the inputs are summed up, which is also called the activation A, and transformed through an activation function, for instance a sigmoid function. The choice of the activation function is determined by the nature of the data and the assumed data distribution of the target variables. The resulting output y hat is then forwarded to the next neuron. However, the human brain, for instance, is comprised of around 100 billion neurons, and each neuron is on average connected with around another 6,000 other neurons. So the question is now, how are they connected? And the connection between two neurons is called synapse. The synapse transmits the emitted electric potential from the presynaptic to the postsynaptic neuron. But it not only transmits the signal, the synapse itself also adapts depending on its utilization. For instance, if we practice something, the same synapse between any two given neurons is activated repetitively. When used repetitively, the synapse transmission improves and the action potential is amplified. Through this amplification, the influence of this connection on whether an impulse is triggered by the following neuron or not is increased, which means, in other words, the specific weight is increased. So learning something means actually just a change of synaptic weights. This connection can also be found in artificial neural networks. The connection between two neurons is equipped with a synaptic weight. And so the magnitude of signal transmission or amplification is replicated through an artificial weight. The larger the weight, the more influential the corresponding input is. In a summation inside the neuron, each input is multiplied with its corresponding weight and summed up. As seen here with C equals W times X. Analogously, for an artificial neural network, learning also means a change of synaptic weights. For simplicity and better understanding throughout the presentation, we will introduce three simplifications. Instead of arrows, we will be just working with connection lines, but the logical flow remains the same from left to right. The weight along the connections is only represented by a W, and the whole functionality of a neuron is consolidated in just one circle. Alright, before we move on, let's take a second and pull together the key learnings of this section. First, artificial neurons just mirror the functionality of its biological counterparts. Second, with a neuron, two key activities are performed. First, a summation happens, followed by transformations. And lastly, learning is done through increasing or decreasing synaptic weights. So going back to our roadmap, we have now covered the first block about the origin. But we still don't know how a neural network really looks like. So let's continue with the second part about the architecture. The architecture of an artificial neural network defines how its several neurons are arranged or placed in relation to each other. However, there's a large number of different architectures out there. And here you can see just the most common types. Due to the limited time, we will only focus on the two most basic architectures, which is the single-layer feed-forward network and the multi-layer feed-forward network. So let's get started with a single-layer feed-forward network. Every neural network is built out of at least two layers. There's an input layer which receives signals from the external environment, which you can see on the left, and there's an output layer to produce the final network output, which you can see on the right. However, real neural functionality with activation and transformation is not performed within the input layer. That's why the input layer is represented in another color and not in the same color as the real yellow neurons in the output layer. The gray input part in the input layer is a bias neuron, which is added to increase the flexibility of the model to fit the data. So now let's dig a little deeper and see how this really works. For simplicity, we'll just look at one specific neuron y hat 1, 1 and assert an observation at 1. As already explained, the first step is a summation, or also called the activation A, in which the inputs are multiplied by the weights and summed up. The sum is called A11, and the activation is followed by the transformation, in which the activation is fed as input into an activation function, for instance a sigmoid function. And these two formulas can be consolidated into just one single formula, which describes the whole functionality happening from the input layer to the output layer for one specific neuron and for one specific observation. But how does this help us in any way? The following example of a multivariate linear regression will exemplify for what such a small network can already be used for. Let's take the basic formula with a typical regression coefficients b, including b0 as intercept. This can easily be replicated by a simple single-layer network. We only need to apply a linear activation function resulting for a certain input and a certain neuron in the following simplified formula. And when we compare the components of both formulas, we can see they match. Such a simple network can however be used for even more, as shown in the next example. Let's take a simple bond pricing model for specific maturity, with the interest rate R and the parameters A and B for specific maturity. Of course, this would actually mean that we would need a different network for each bond maturity. But since we are talking here only about a simplified example, this is also doing the job. If we take the network from the previous example, we only need to do minor changes to replicate the bond formula. We need only one input neuron and replace the linear activation function with an exponential function. And see, the components of both formulas match. And we are able to replicate the bond pricing model. So, at this point, I would like to thank you for your attention and would like to hand over to my colleague Maxime, who will guide you through the remaining part of this presentation.
Thank you, Julian. Let's now consider more complex structure. We still have input and output layers before, but now we build a network with many hidden layers, which is also known as a deep learning structure. This architecture allows us to better understand a very complex structure of the data. In the following, we are going to use one hidden layer with 3 hidden units. Let us now build our network based on our two-dimensional data example. We take 2 inputs, x1 and x2, and also the output y. Let's look closer how the multi-layer network architecture looks like. To do this, let us first take a look at the first hidden layer. Each input value x, we need to multiply by a corresponding weight and then add it together with all other results for each neuron. As a result, we get the activation of our first layer, A1. After we get the activation of the first layer, we need to apply the activation function. After applying the activation function for A1, we get Z1. This is a complex operation, but if we take the 3 outputs we are looking for as a single row of a matrix and place all our individual weights into a matrix of weights, we can create the exact behavior we need by multiplying our input data matrix by our weight matrix. Matrix notation is very helpful here because it allows us to express a complex underlying process only in a single line. To finish forward propagation, we need to propagate Z1 to the output y hat. So we have already calculated Z1 in the previous layer. So all we need now is to multiply Z1 by corresponding second layer W2 and applying again the activation function. So we get 4 equations, but we can think of them as a one big equation. We express y hat as the activation function of A2 and A2 as a product of Z1 and W2. We can again rewrite Z1 as an activation function of A1. And we also know that A1 is just a product of input x and the weight from the first layer. Now, it's clear to see that our neural network is a function of input and weights of hidden layer 1 and also of hidden layer 2. This particular neural network model comprises 2 stages of processes, but in general it's possible to add any number of hidden layers in the model. For this reason, the neural network is also known as a multi-layer perceptron. Please note that this function is differentiable with respect to the network parameters, and this property will play a central role in a network training. The big advantage of the neural network is that they compute any function at all. No matter what function we want to compute, we know that there is a neural network which can do this job. As an example, you can see on this picture the capability of multi-layer perceptron to approximate 4 different functions. In each case, observations include 50 different points, shown as the blue dots. These data points were used to train a 2-layer network with 3 hidden layers, using tongue activation function and linear output units. The resulting network functions are shown by the red curves, and the output of each 3 hidden units are shown by 3 dashed curves in purple, green, and light green. So what we have done so far? We have seen that even with a simple structure, neural network can efficiently solve simple problems, and adding hidden layers make it possible to solve even a complex problems. Additionally, a 2-layer network with linear outputs can uniformly approximate any continuous function. Let's go back to our roadmap. We have already seen the structure of the neural network, but we still don't know how to estimate the parameters. Let's move on to the last part of our presentation. So far, we have seen how neural network works, but now we need to take a closer look at our prediction. To evaluate the model, we need to quantify exactly how wrong or how well our prediction is. To do this, we need to take a closer look at the cost function. In the literature, there are a lot of cost functions that can be implemented by the training the neural network. In this example, we will use a sum of squares cost function, which can be calculated by taking each error values, then square it, and add these values together. Multiplying by 1/2 will make the calculation simpler, it will not change the results. Now we need to minimize the cost function. For this, we need to take a closer look at our cost function. Our cost function is determined by 4 different factors: output and input, which are given, activation function f, which we need to choose depending on the nature of the data, so the only one thing that we can affect in our model are the weights. So we minimize the cost function by changing the weights. So let's plug our derived equation in the cost function. We can see that the cost function is a function of weights on our synapses. We don't have much control on our data, but the only one parameter that we can change are the weights. So we'll minimize the cost function by changing the weights. Now we are looking for some combination of weights that will make our cost function j as small as possible. We want to know which way is downhill, that is, what is the rate of change of j with respect to w, also known as the derivative. And in this case, since we are just considering one weight at a time, the partial derivative. We can derive an expression for dj dw that will give us the rate of change of j with respect to w for any value of w. If dj dw is positive, then the cost function is going uphill, and if dj dw is negative, the cost function is going downhill. This method is known as a gradient descent. However, this method has the following limitations. What if our cost function doesn't always go in the same direction? What if function goes up and then go down, meaning that the cost function is not convex? In this case, we will get stuck in the local minima instead of the global minima. For successful application of neural network, it may not be necessary to find a global minima, but it may be necessary to compare several local minima in order to find a sufficient limit. Let us implement the gradient descent to train our network. Our weights W are split into 2 matrices, W1 and W2. We'll separate our computation in the same way by computing djdw1 and djdw2 independently. We should have just as many gradient value as weight value. So when we've done, our matrices djdw1 and djdw2 will be the same size as w1 and w2. Let's look at djdw2 first. First of all, we need to plug in our cost function. Now we can simply calculate the derivative. The power rule tells us to bring down our exponent 2 and multiply it. To finish our derivative, we need to apply the chain rule. So we take the derivative of the outside function and multiply it by the derivative of the inside function. Y is the output that doesn't change, so the derivative of the y with respect to w would be 0. Y hat on the other side changes with respect to w2, so we need to apply chain rule and multiply our result by dy hat dw2. So now we need to compute the derivative of the y hat with respect to w2. We have seen before that the y hat is an activation function of a2. We express the chain rule as a product of the derivatives. We break dy hat dw2 into dy hat dA2 times dA2 dw2. To find the rate of change of y hat with respect to a2, we need to differentiate our activation function with respect to a2. So it's known that we can replace it by f prime a2. So now we need to calculate the last term, dA2 dw2. This term represents the change of A, our third layer activity, with respect to the weights in the second layer. A2 is just a linear function of z1 and weight w2. We can simply calculate the derivative and get z1. We rewrite the green part of the equation as a delta 2. And finally, we get our results. Now we need to compute the final term, djdw1. We use the same approach as before. First of all, we compute the derivative through the final layer. First dj dy hat, and then dA2 dw1. Now we need to take the derivative across our synapses. There is still linear relationship along each synapses, so we get the derivative for dA2 dz1, which is w2. Applying again the chain rule and use the linear relationship, and we get the following expression. We define a new parameter delta 1, and we get our final equation for dj dw1. Let's now pull together what we learned today in one algorithm. In the first step, we propagate the input through the network to make the estimation of the output. Once we estimated the output, we need to evaluate the output by computing the cost function. In order to minimize the cost function, we backpropagate the error to each weight by multiplying the activity on each synapse. The weights that contribute more to the overall error would have larger activations, which will lead to larger djdw2 values and will be changed more when we perform the gradient descent. We repeat these steps until the network performs adequately. So what we have learned so far? We train a neural network by minimizing the error. Only one parameter that we can affect are the weights. The weights that contribute more to the overall error would be changed more when we perform the gradient descent. If you want to know more about neural network, we would like to suggest you some useful and interesting sources to go deeper in this topic. The first source focuses on the architecture of multi-layer neural networks and helps to understand the basic intuition behind the hidden layers. The next one is a more complex example with detailed explanation of backpropagation and related deviations. The third source is an excellent playground. Users can find 4 different datasets for classification and several parameters to play with. It's a great platform to develop your intuition and to get a general overview how neural networks are constructed. The last, but not the least, if you are interested in the implementation of the artificial neural network in finance, we would suggest you the following paper, which deals with the implementation of neural networks for forecasting of stock market trends. So it was a rough overview how the neural networks are constructed. Thank you for your attention, and we are looking forward to your question.